Welcome, everyone. You are signed on to the Precision Digital webinar titled The Fundamentals of 4 to 20 milliamp Current Loops. This is the first webinar in a series of 3. The series is about 4 to 20 milliamp process signals. This particular webinar is designed as a basic course for those folks who out there who deal with 4 to 20 milliamp signals and loops and currents, but are not full-fledged electrical engineers. Naturally, if anyone out there today is an electrical engineer, we're happy to have you on board too. General housekeeping items. The most common question we get from folks is, will I get a recording, or will this be available as a recording after the live broadcast? The answer is yes. Everyone who registered for the webinar will get an email, probably go out within 24 hours of this broadcast, and the email will include a link to the recorded version and the slides. Additionally, we'll be posting a link to the recording on the Precision Digital website, but that won't be available probably for a few days. So look for the email shortly within the day. Everyone who's signed on today is in listen-only mode. That means we've muted everybody's phone from our side, so there won't be any live voice interaction. We've got too many folks out there to be able to do that today. So everyone's phone is muted. So you can make as much noise as you want. It won't bother anyone else, at least on the webinar. Questions. We encourage you to ask questions as we go through the webinar. You don't have to wait for the question and answer session to type in your question. If you look in your control panel in the lower right-hand side, you'll see a little tab that says questions. Just open that up, type in your question when it comes to mind, and if it's something short and uneasy, we'll answer it right away. Otherwise, we'll keep a list of the questions to address during the 2 question and answer sessions. And if we don't get to your question, it doesn't mean we're ignoring you. It means we just have too many to address in this short time period. And we'll promise to get back to you after the webinar if it's a question we don't get to during. This webinar is booked for an hour, I know, on your calendars, but we've got this time, so it should be completed with everything in 45 minutes. So we'll give you a few minutes back. Okay, presenters today. This webinar is presented and produced by Precision Digital Corporation. Precision Digital designs, develops, and manufactures a full line of digital panel meters and associated devices. And we don't talk about the products during this webinar. This is an educational webinar, so it's not a pitch for products. But naturally, if you have questions about digital panel meters or something, we'd love to hear from you. Give us an email or give us a call after the webinar, and we can talk at length about the products. Anything from panel meters to temperature controllers to annunciators. But again, we don't talk about the products during this webinar. Speaking today, my name is Bruce McDuffie. I'm your moderator today. I'm with the Precision Digital Marketing Department. Don't hold that against me. I'm your moderator today, and I'm speaking to you from Boulder, Colorado. Our main presenter is Joe Ryan. Joe is the product manager with Precision Digital. He has more than 10 years of experience with process signals and design, support, manufacturing, and such, and manufacturing of process measurement and control devices, and he has extensive field and support experience with 4 to 20 milliamp signals and loops and devices. Joe's our subject matter expert today, and he'll be your main speaker. Joe's speaking today from the Precision Digital headquarters in Holliston, Massachusetts, which is just east of Worcester, Mass. And third, not a speaker, but supporting today is Ryan Shea. Ryan is working behind the scenes. He's the one answering your questions. If it's as I said, if it's a short question, he'll be responding quickly to those and managing that window. Ryan's an application specialist for Precision Digital, and he is supporting customers on a daily basis with their 4 to 20 milliamp questions, so he's also an expert in that technology. Ryan is speaking from the Precision Digital headquarters in Holliston, Massachusetts. And with that, introductions made, I'm going to turn it over to Joe to kick off what we'll be covering today. Joe?
All right, thank you, Bruce. So first, why don't we take a look at what our objectives and takeaways are for our webinar today. We're really hoping that you leave here with an understanding of three things. The first of which, obviously, is the fundamentals of the 4 to 20 milliamp current loop. That's what is a current loop? Why is it 4 to 20 milliamps? What are the things you have to be aware of in order to work with it? We want you to be able to choose the correct devices and instruments that go into that current loop. There's specific devices that are always going to be present in a current loop in order to make it happen, and you need to have an understanding of what those are if you're going to be able to work with current loops. And the last one is being able to spot if a 4 to 20 milliamp loop is the right choice for your process need. It's an industrial standard that's extremely common out there, but it's not great for every application, and some applications that should be 4 to 20 loops may be currently being used as something else. So to do that, we're going to follow the agenda you see here. We're going to define the 4 to 20 milliamp current loop. Again, a discussion of what that actually means. We're going to discuss the individual components at length. We're going to review the pros and cons so that you'll know why people use it, but also why sometimes they don't. And we'll let you know what the essentials are you should walk away here from, so that if nothing else, you can know what to keep an eye out for when you're out there in these process applications and you have the opportunity to work with a 4 to 20 loop. But Bruce, before we get into the content, you had a few questions.
Yeah. I know on webinars it seems like you may be the only one listening, but I think it's kind of fun and interesting to find out, get to know who's out there listening today. We've got more than 300 people signed on right now, so we have a great, diverse group. I've got 3 quick questions, and I hope you find these interesting. The first question is, where were you located? You can select one of the major regions, and everybody just go ahead and click and vote, and we'll see where the audience is today, and then I'll share the results, of course, so we can all see. So we've got everyone's voting fast and furious. That's good. We appreciate your input on that. So we've got about 80% voting. Slowing down a bit now. It's a pretty easy question, I think, but let's start off with. Last chance. Wow, 90% voting. That's great. Okay, I'm going to go ahead and close the poll. Here's the results. Looks like Eastern U.S. is the big contender, or participant today, 43%. Central U.S., 28%. Western U.S., they're probably still waking up out there, 16%, and see folks in Canada and other countries. Great, thanks. Let's go on to the next question. What industry? What is your industry? Select one of the following if it applies: public utility, oil and gas process, industrial distributor, manufacturing, or other. And this one you can only pick one, so if you're in a couple of industries, pick, I guess, your most important one, or your favorite if you prefer. Votes are coming in, about 85% voting. Thanks again for participating. Looking like industrial distributors and other. Guess we got to work on our list, Joe. Other is a big one. Okay, I'm going to go ahead and close the poll. Thank you. And you can see the results. Industrial distributors, pretty good, really good mix. We'll have to figure out what other is for the next webinar. And last one before we get into it. Question is, what is your level of experience? And this helps Joe tweak the presentation a little bit. He knows what the general knowledge is out there. If we get too many seasoned field experts, it might freak them out a little bit, but no, it wouldn't.
I think we can manage.
Okay. I know you can. You can pick, no, that's a later one where you can pick multiple. You still have to just pick one here. Okay, about 90% voting again. I'll go ahead and close it. Last chance. Okay. Looks like about half the folks know enough to get the job done. Good. Some novices and a few seasoned experts. Great. And a few electrical engineers. Good. Again, it's a great mix. So thanks for indulging us on that. Everybody, we've got a couple more polls. We won't kill you with the polls, but we just have a few that we think are interesting. So Joe, it's all yours. Yeah.
And that's a good mix. I'm glad to see that there's some novices, there's some people who know just enough to get it done, and hopefully both groups will learn something here today. To the rest of you, hopefully this will be a good refresher, or maybe touch on something you haven't thought about in a while. So let's dive right into the content here. With what is a 4 to 20 milliamp current loop? Well, it's a current loop, obviously. And in order to understand how that current loop works, I want to touch on the only equation we'll talk about here today, which is V equals IR. And that's the fundamental electrical engineering equation, that voltage is equal to current times resistance. So anytime you have one, you want to have all of those, and this explains how they interact with one another. Now, the important thing to understand about these is how they interact in a circuit. So we've got a very basic circuit diagram up here. On the left of the diagram, I've got my VTOT, and that represents what's providing the voltage to make this circuit run. In most cases in the process industry, you're going to find that that's going to be a DC power supply of some kind, although it could also be a battery or any other voltage source. Then I've got the different elements that are connected up in my current loop. I've got R1, R2, and R3, which are modeled as resistors, but really could be any kind of load. That could be a panel meter or a PLC. It could be a transmitter, a chart recorder, anything that is connected up to that loop. Each one of those devices, because it has a unique R, is going to have its own voltage drop. So my VTOT is my power supply giving the voltage to the loop, and then I lose voltage at R1, R2, and R3. The critical thing to understanding why the current loop is so popular and how to wire it up is that you'll see there's only one I, and that's the dashed looped arrow running through the middle of this circuit. I is the same everywhere. Every element here has a different resistance or impedance, and every element has a different voltage drop or is providing the voltage, but the current is the same anywhere. So if I measure that current between VTOT and V1 in this circuit, it's the same as if I measured it in between V2 and V3. And that's the big strength of this current loop, which we'll discuss in a little bit. One convenient way to think about current loops and circuits in general is in a flow analogy, which is something that a lot of people have a much more intuitive understanding of. In this circuit on the left, my VTOT is the power supply, which can be modeled as the equivalent of a pressurized water tank, and that's what you see here in the picture. The resistors, the loads on the circuit, can be modeled as, for example, we've just got a simple water wheel here. It could also be modeled as a pipe restriction or any other element in the flow system that's going to impede the flow of that water trying to leave the tank. The current is essentially the flow of water. So I've got this potential built up in my pressurized tank. The water's trying to escape. It wants to equalize down to zero pressure everywhere, but it's hitting these restrictive points like the water wheel, where I'm going to have water pressure backed up on one side and not the other. So with pressure being my voltage, you can see where I would get a pressure drop on each side of that water wheel. The pressures would be different. But the flow throughout the pipe's the same. The same water I have going into the pipe from the tank is the same flow of water I have pouring out the bottom of the pipe after the water wheel. So current's the same everywhere in this circuit, even though I've got different voltage drops across the different resistive elements. With that basic explanation out of the way, let's talk a little bit about how we got to where we are and why people use this. This technology, the 4 to 20 loop, started appearing in the 1950s. It was influenced heavily by the pneumatic systems that existed at the time. Those generally would use compressed air as a control, and everything would be mechanical. You would have pressurized air tubes running all throughout your plant, controlling your processes and transmitting that information. Those usually would be in the range of 3 to 15 psi, though it could vary. And much like the 4 to 20 milliamp signal, you'll notice there's no 0 there. And there's two reasons for that. The first is that modeling a 0 milliamp output from something was very difficult to do. While it's easy to get 0 milliamps, it's an open circuit where there's no current flow at all. The problem is the low ranges. Trying to get something that could sweep from, say, 20 milliamps all the way down to 0, passing through the 1 milliamp, the 0.5 milliamps, the 0.1 milliamps. Designing the circuitry to do that was very difficult and expensive, especially back then. The other reason, and this is something that the pneumatic systems took advantage of, and 4 to 20 just decided to do the same, is that by making your 0% signal 4 milliamps, you know when the difference is between, or you know what the difference is between a 0% signal and some kind of failure in your system. So if I have 0 milliamps on my line, or I have 1 milliamp on my line, I know I have some kind of problem. I have a device that's wired wrong, I have a break in my line, something is going haywire, because even at 0, I should be seeing 4 milliamps. If I had that 0 to 20 milliamp range, then I may think that my system is just off and I'm getting a 0% signal, but in reality someone's broken a wire, or I've lost power, or there's been some kind of other failure. If you find this topic fascinating and you want to do a little bit more reading on it, you can find the industrial specification up on your screen, and I'd encourage those of you who really want to dive into this to go take a look at that, although it's not particularly engaging reading. So what is a 4 to 20 milliamp current loop in terms of a process control loop, let's say? Well, you have to understand the different components that make it up. And the first one's going to be the sensor, which is that thing that's providing some kind of output based on your actual measured process variable. It actually is in contact with the material that's going through a flow meter, or it's the thermocouple connected to whatever the temperature is being read from. You've got a transmitter. The transmitter is what's responsible for actually creating that 4 to 20 milliamp signal and regulating it. And then you've got some kind of receiver, or multiple receivers. In the graphic here, we've got it being a process controller, but it could be any number of devices. The last element is the power supply, which may or may not be an entirely separate device. And I'm going to go a little bit more into detail on each of these now so that you can have a better understanding of how these all interact. The first element is the sensor. This isn't actually part of the 4 to 20 milliamp current loop itself, but obviously it's a critical component. This is what's actually measuring whatever it is you're trying to provide a 4 to 20 milliamp output from. In the case of a flow system, this could be a turbine flow meter that would provide a small millivolt pulse output. It could be a thermocouple or an RTD that's actually in contact with something reading the temperature. It could be the optical encoder that's reading pulse outputs from something that spins, or it could be the actual ultrasonic emitters on an ultrasonic level transmitter. So it's the often unique and specialized technology that's getting you your process variable into your electrical system. Generally, they'll do that by outputting some kind of voltage, and in that case, okay, you could just try to use the voltage instead of a 4 to 20 loop, but there's a lot of issues there. You have issues with how far can it run before the resistance of the wire becomes a problem. How affected is it going to be by noise? Is it a useful signal at all? In some cases, the signals are so small and so subject to outside interference that you really couldn't do anything with it anyway. Systems such as radar level readings really need to be transmitted out as something else in order for them to be fully understood. They have to have complicated timing circuits in there. So the sensor can be fairly complicated or pretty simple, but it's never ideal to work with that signal being output. And that's really where your transmitter comes in. The transmitter and the sensor are often the same thing, although sometimes they are different components. You could have a separate thermocouple and a temperature transmitter, for example, that are two different things that could be bought separately, but you could also have a radar level gauge or radar level transmitter where they're combined into one device you purchase. The purpose of the transmitter is to take that unique signal that's measuring your process variable and use it to regulate the 4 to 20 milliamp signal. So what the transmitter does is say, all right, well, it's developed so that at 0% of whatever its measurement range is, you're going to get 4 milliamps. And at 100% of whatever its measurement range is, you're going to get 20 milliamps. Most of the time, those 2 points are connected by just a simple linear line. So if I'm looking at the scaling example shown here, I would have a level transmitter that's designed for 100 feet. And when I'm at 0 feet, my level transmitter is going to be outputting 4 milliamps. When my level transmitter is detecting that there's 100 feet, it's going to be outputting 20 milliamps. And then it just connects all the points in between. So if I'm at 50 feet in this tank that I have this transmitter on, it's going to be outputting a 12 milliamp signal. The transmitter regulates the current in the loop. The power supply is what provides the voltage to make that current possible. Because remember, your V equals IR. In order to have a current there, you've got to have a voltage. This is always going to be a DC power supply. When you hear 4 to 20 milliamps, what they really mean is 4 to 20 milliamps DC. And in most process applications, people use a 24-volt power supply simply because it's the most common and convenient. You can run into others, though. There's 9, 12, 15, 36 volts. There's probably some other oddballs out there that you'll run into as well. But the idea here is that all they're doing is providing the DC voltage. They're not regulating the current. That's the job of the transmitter. The critical part about the power supply is that whatever voltage you're providing, it needs to be higher than the sum of the voltage drops in all the other elements of the loop. Usually that's not a problem. If you don't work with any 2-wire or loop-powered devices, you may not even have to worry about this, and you may not even think about it in your day-to-day affairs. However, if you're using 2-wire or loop-powered devices, this becomes really critical. You want to make sure that you're not using a 2-wire transmitter, meaning that it draws its power off of the current loop, and that transmitter might require an 18-volt drop, but then trying to run it with a 9-volt power supply. Because regardless of how small the voltage drops may be in all those other pieces of equipment, that 18 volts in your transmitter is going to sink that 9-volt supply, and now all of a sudden your system's not going to work. So it's critical, especially in cases where you're involving 2-wire devices, that you know what your voltage drops are going to be, so that you know if your power supply is going to be able to support that loop. And if not, you have to look to something else. You either need to get devices that are externally powered by something else other than the loop to lower their voltage drop, or you need to get a power supply that provides more voltage. Then you've got the receiver or receivers. The job of these is to receive that current signal. These are your panel meters, your chart recorders, the inputs into a PLC, the input cards on a SCADA system, essentially anything else that is reading that current loop. And usually what these will do is internally, invisible to operators or installers, they'll have some kind of small sense resistor, and using that voltage equals current times resistance equation, they can calculate out, well, I have a microcontroller, say, inside of this, or some kind of simple electronics that reads the voltage drop across my small sense resistor, and that's going to allow me to calculate out what the current is. And then there's some kind of programming you usually do, such as scaling it for the display values, that allow it to act on that information. Sometimes that's just displaying or recording that information. Other times you're going to have additional outputs from these receivers that could be relays for alarms, or they could be serial communication signals to your control system. It may even be an additional 4 to 20 milliamp loop that's scaled differently that goes off to some other devices somewhere. So the receiver is one of any device that is going to be on this loop, but they all have somewhat similar characteristics. You want to be aware of their input impedance, their voltage drops, and none of them are going to actually be regulating your current. That's the job of the transmitter and the power supply. One thing I'll make quick note of is that oftentimes either the transmitter or the receiver will have a power supply built into them. That's why sometimes you don't need a separate one. The panel meter you see here, for example, that's a Precision Digital ProView panel meter. If you're powering that from a separate DC or AC voltage, it includes a 24-volt power supply that's isolated from that other supply for you to use in powering up your loop. So in a case where you have a meter like this, you don't need a power supply because the power supply is built into one of your receivers. Similarly, there are transmitters that get powered by some other external supply that's not a part of the 4 to 20 loop, and therefore they use that to provide power that you can use to run your loop. The last component is something that generates a lot of questions, but oftentimes isn't really relevant. So I want to take a minute to talk about the wire that you use to run your loop. So wire does add resistance to your loop, but the resistance is extremely small. The chart here shows, based on your wire gauge, how many ohms in resistance you get of wire. So if you're using standard 12-gauge wire, and you've run 1,000 feet of this, you've only got 1.6 ohms. Even at 20 milliamps, if you walk through that voltage drop is equal to current times resistance equation, you're going to see that you're going to drop around 30 millivolts off of that 1,000 feet of wire. Well, if you're using a 24-volt supply, 30 millivolts is not going to cause you a problem. And unlike a voltage signal for control systems, because current is the same everywhere in the loop, you don't get any added inaccuracy because of that voltage drop either. The same milliamps that are being put out by the transmitter are going to be the same that are arriving at your receiver, regardless of what the wire may do to resistance or voltage drops. So in a 4 to 20 system, you really don't need to be concerned about the wire unless you are running really close to that voltage cap, which is I generally recommend against anyway. And Bruce, you had a couple questions about the audience.
Yeah, that's good stuff, Joe. Thanks very much. We'd like another question for the audience, a polling question, and then we'll open it up. We've got a few questions coming in via the question window that we'll take. So if something comes to mind even now, go ahead and type it in the question window, and I'll be posing those to Joe here in a minute. This poll is, what is your primary application for monitoring and or remote metering? And you can select more than one application here if it applies. So if everyone could go ahead and vote and choose your applications. It's like a really, really wide selection on this one. So far, temperature and or pressure are leading. %, voting. Keep them coming. This one takes a little bit longer because you may be selecting more than one. Looks like most folks are in. Okay, last chance. I'll go ahead and close the poll and share the results, and everybody can see there's a good mix. Not too many others, so that is, we picked those ones pretty well, Joe. Pump control, level, temperature and pressure, 80%. Next one, flow and level, are about even at 70%, and pump control at 48%. Okay, thanks everyone. Okay, let's have some questions. We have a question from Jean-Pierre in Montreal, and his question is that he recently changed his turbidity transmitter from one that handled 0 to 1 NTU to one that handles 0 to 5 NTU over its 4 to 20 milliamp range. But he only measures from 0 to 0.15 NTU. So since then, the HMI and other equipment, his 4 to 20 milliamp signal goes or has been fluctuating. Could that be noise or something related to his signal? Joe, what do you think?
Well, so just to recap there, so he had a 0 to 1 NTU, which is a turbidity unit measuring flow turbidity, and then he changed out to a 1 to 5 unit, and I'm presuming then that his scale was 4 milliamps at 0 and 20 milliamps at 1, and then he changed it out to be 20 milliamps at 5. if he's only looking at a small portion of that range, then what is likely happening there is he has his receivers scaled such that they're only looking at somewhere between 15 to 3% of the range of his transmitter, and that would be causing him a problem. So originally, if he was looking at 15% of his range, let's say, he could afford to have some noise in that system, whereas now that he's looking at only 3% of his range, all of his process variable ranges that he's looking at are only really going to be varying by about 1/2 of a milliamp. And when you have the entire range that you're trying to display or control in 1/2 of a milliamp and not the full 16 milliamp range, then yes, you become susceptible to additional noise effects. You also run the risk that minor fluctuations in the transmitter's ability to control the current or inaccuracies that are happening while the flow is being measured are going to be much more pronounced. So really the lesson there is you want to use as much of the full 16 milliamp range, the 4 to 20 range of your transmitter as you can. And that means either selecting a transmitter that is properly sized to the range of process variable you're trying to read, or getting one that allows you to scale that range appropriately. So in his case, I'd recommend that he look into one of those two solutions.
Okay, good. Here's a question about one of the slides, Joe. This is from Thomas. He said the slide for the transmitter had acronyms UNA and OVR. Could you say what those are?
Sure, let me go back to that real quick if I can.
Sure.
Just so everyone knows what we're talking about. So in the lower right of the graphic here, you're going to see UNR and OVR. And what that stands for is under range and over range. The 4 to 20 milliamp signal doesn't stop exactly at 4 and 20 milliamps. Most devices, most transmitters and receivers can handle an over and under of some percentage. And then that's usually going to be in the ballpark of, let's say, 5% or maybe 1/2 a milliamp. And the purpose of that is that these things tend not to be precise. You may get a 0 to 100 foot level transmitter, like the scaling example that's given here, but based on where your pumps are going to have to go at the bottom of the tank and where you calibrate the 0 to, there's a chance that you're going to actually go under the 0 that is 4 milliamps. And similarly, there's a chance you could end up going over the limit that you have set up to be your 20 milliamps. And so in those conditions, most devices have conditions they can be set up for, such as, well, if you go over 20 milliamps, I want you to set off these alarms. Or if you go under 4 milliamps, I want you to continue to display 0 and not go negative. So those over and under ranges are built into all of the devices that go into this 4 to 20 milliamp loop and usually have different behaviors associated with them.
Okay, good. We have a question here from Mike. Mike says, what do you mean by regulate the current when you say the transmitter regulates the current? Okay.
So you have this equation of voltage is equal to current times resistance. And that would mean that your current, if I do a little algebra to it, that would mean that my current is actually going to be equal to my voltage divided by resistance. If that's the case, and your resistance doesn't change, then you just have a current you can calculate out. So if I just build a simple circuit with a battery and a couple of resistors, I can do some basic math and tell you what the current's going to be all throughout that circuit. But this is a 4 to 20 milliamp range. That's what allows me to transmit different process variables to other pieces of equipment. That's what gives me the ability to transmit either my 0 feet or my 100 feet or my 4 milliamps to my 20 milliamps. So what the transmitter does is it regulates that current. So I've got the power supply that's just putting out as much current as it can to support whatever resistances are in the loop. But something has to be variable in there, and something needs to essentially dial in what the current needs to be. And there's current control circuitry in the transmitter that is used to regulate what current passes through the transmitter. And because current's the same everywhere in the circuit, that current that passes through the transmitter is the same current that's going through the rest of my loop. So the transmitter is what's responsible for controlling what current is allowed through it, rather than essentially having no control over the current, in which case you wouldn't have a means to transmit a process variable. You have to have something in there that actually regulates the current. Using that flow analogy, the transmitter would actually be a valve that you were opening or closing to regulate how much flow at any given time was going to be allowed through your pipe.
Okay. Great.
Hope
Thanks.
that answers your question.
That valve one really makes it relevant. We've got time for one more question, and then we'll have to move on. And this is from Chris. Chris says, correct me if I'm wrong, but passive loop means you provide the 24-volt power supply, and active loop means 24-volt power supply is built in.
You are absolutely correct. The general terminology is that if I have a passive loop output, then I have all of that current control circuitry, but I don't have any voltage power supply built in. So I can regulate a current if you give it voltage, but that's it. An active output has some kind of integrated power supply into it. So you likely will have those same two pins. You'd have your plus and your minus for your output, but now there's a voltage supply built into the transmitter, and it's going to be driving that current out. So you don't need an external power supply.
Okay, good, great questions. Keep them coming. We have a few more slides to go over with Joe, and at the end we'll have another session with some questions. And so great. It's all yours, Joe.
Okay. So now hopefully we have a fairly good idea of what makes up that 4 to 20 loop and how it functions. Let's talk about why people choose to use it. The number one reason is that it's simple to wire and configure. Because you're just making one big loop with your wires, it's easy to connect those up. All of your devices will only have 2 pins on them, a plus and a minus. And if you do have a problem in your circuit or you want to trace how it works, all you're doing is just walking your wires around this loop, making sure that everything's connected properly. It tends to use less wires and connections than some other possibilities. If I were to compare it to something much more complicated, let's say I had a Modbus device, which is a serial communication protocol, and it's talking on 5-wire RS-485. Well, now these are more complicated terms I need to know. I've got these 5 terminals on all my devices. I have to wire this up as a big serial bus that gets very complicated and hard to follow if you have problems. 4 to 20 is much simpler when it actually comes to doing the wiring. Longer distances are okay without losing signal as opposed to voltage output signals. You'll recall that the wire isn't really relevant to a 4 to 20 milliamp loop in almost any case. It does have a voltage drop associated with it. So if instead of a 4 to 20 signal, I was using, say, a 0 to 10 or a 1 to 5, well, now I'm measuring voltage, and I may have some kind of a voltage transmitter that would regulate my voltage at the transmitter, but then I would have a voltage drop across the wire and other components. And now I have a problem because my receiver's not getting exactly what I'm outputting from my transmitter. You avoid that entirely by going with current, because current's the same everywhere in the loop, whereas I'd have wire voltage drops and junction voltage drops everywhere else. It's got a low sensitivity to electrical noise. That's very important for applications in, let's say, flow, where you have a millivolt signal coming out of a flow meter, and you can't do much with it. You can't take a millivolt signal and run it very far because you have all sorts of noise problems. Similarly, a thermocouple is essentially measuring a millivolt signal, and again, you can't run it very far without running into all sorts of problems. 4 to 20 lets you avoid all that. You can run it long distances. You will pick up some noise, but because it's a powered signal, it's unlikely to affect it very much. And lastly here we have, it's easy to detect the loss of signal or power. That goes back to this idea that if I have 0 milliamps, I know there's a problem. If I have a 0 to 10 volt signal, well, is that 0 volts? Is that open circuit? The fact that I wired it wrong? Did some device lose power? You don't know. With 4 to 20, you always know if your wiring is correct, and you generally know if your devices are functioning or not. So with all those pros, why wouldn't you use a 4 to 20 signal? Well, the biggest reason is that you only get one parameter transmission. And what I mean by that is that you have a 4 to 20 range that can send out one variable. It could be transmitting a temperature. It could be transmitting a level or a flow rate. It could be transmitting a speed. But each 4 to 20 milliamp loop can only send information about one of those variables. If I have something along the lines of a multivariable level transmitter, where I have one transmitter that's capable of measuring the top level in my oil and water tank, the interface level between the oil and water, and the temperature of the material in the tank, well, I would need 3 separate 4 to 20 milliamp loops in order to send those 3 pieces of information via the standard 4 to 20 protocol. If I have 5 tanks and each tank has 3 variables, now I'm up to 15 loops I have to somehow manage. So as you get more and more complicated with the information you're trying to acquire, it might be time to start looking at other things, such as including HART, which is a serial protocol that runs on top of a 4 to 20 signal, or Modbus, which I mentioned earlier. Things start to get complicated, and all of a sudden you're finding yourself managing a large number of loops, and in those circumstances there may be better alternatives. And the last 2 bullets here under con tie together, which is susceptibility to ground loops and the isolation requirements to avoid them. I could present an entire webinar on ground loops and isolation requirements, but for the purposes of the fundamentals, I'll sum it up by saying that when you have devices in your loop that accept or transmit multiple 4 to 20 milliamp signals, so for example, if I have a block of PLC DIN rail mounted units and I bring in 8 4 to 20 milliamp loops into those, I need to be very aware of whether or not they all share common pins, if their minus terminal for all those loops are tied together, and if a isolated power supply is required. Because if I'm not, I could get all sorts of strange ground loops where all of a sudden, instead of having isolated loops which transmit their values nicely, I start sharing current between loops, and then you're going to get all sorts of problems. You're going to get signal averaging problems. You're going to get voltage supply problems. You open up the door to a whole bunch of different problems that are going to be hard for you to diagnose. So again, when you start getting a complex system that's using multiple 4 to 20 loops all going through one device somehow, you need to take a step back and be very careful what you're doing. But for simpler applications, the 4 to 20 loop is an industrial standard for a reason. And that's the first essential you need to know when it comes to takeaways from this webinar. It's an industrial standard for a reason. It's simple to use, and with a little bit of study, almost anyone can get it. So if you can use it, you probably should. Some considerations when choosing your devices, especially with 2-wire devices, you need to be aware of that loop drop. You need to know what that voltage drop is so you can make sure that your power supply supports it. You need to make sure that if you have a device that has multiple 4 to 20 milliamp loops going through it or from it, that you have the isolation requirements met. And you need to be aware of how many parameters you're going to try to be transmitting in your system as a whole so that you can plan accordingly for it, because you need one loop, one transmitter for each one of those parameters you're trying to send. And lastly, when can you not use 4 to 20 milliamps? Well, essentially anytime you don't have a transmitter in the system. If I have pulse outputs coming from a flow meter or a rotary encoder, or I have a thermocoupler RTD, I have a pressure gauge that needs to directly measure pressure on the inside of a pipeline, then I don't have a transmitter to get me into the 4 to 20 milliamp world. And my choices are either find a piece of equipment that will connect up to whatever that sensor is, or find a transmitter that will connect up to those things, and then bring me into the 4 to 20 milliamp world. But once you start seeing that you're directly connecting up to a sensor and not a 4 to 20 transmitter, you have to start planning a little bit more to decide whether or not you need to get it in the 4 to 20 world or equipment that's available to work with what you have. So to sum up, we talked about the definition of the 4 to 20 milliamp current loop, what the different components are that make it up. We discussed the pros and the cons, There's a lot more pros than cons, especially for simpler systems. And we talked about a few things for you to keep in mind when you start working with these loops. And Bruce, before we wrap up, you had a question?
Yeah, thanks everyone. As we're looking at this, we're going a bit longer than the discussed 45 minutes, but hopefully you got an hour booked out in your calendar anyways. So we're just going to keep going, and we have a lot of great questions from the audience coming in. So I think we'll have a really interesting question and answer session here after the poll. This is the last poll. Question is, how often do you specify digital displays? Now, don't panic. We're not going to jump on you with our sales team and if you put something down here. This is only for information. There isn't any sales call follow-up after this webinar. We just want this to be educational, and of course, we want you to think of Precision Digital when it comes to digital panel meters and so on. So please feel free to vote honestly and authentically, which I know everyone will. And you don't have to vote. It's not mandatory. But if you feel the desire, go for it. So it's about 70% of the folks are voting so far, so great. Good deal. So I hope you're finding this interesting. Again, like I said, we have some really good questions coming in, so hopefully you can stay on and hear them. Okay, looks like everyone's voted who wants to. I'll close out the poll. You can see the results. So again, a good mix. This is a great diverse audience today. Most folks 3 to 10 times a year. Few folks never. And that's okay. All right, I'll hide the results, and we'll go to the questions. Okay, see what we have here. There's a question here on, can you review how you would connect a 3-wire probe to a 2-wire loop-powered controller?
Sure, I can give a brief answer to that with the tools that are available. We'll talk about it a little later, but we have a few other webinars scheduled that will answer that question a little more in depth. And you'll pardon me for going back to an earlier slide to answer that. So a 3-wire probe versus a 2-wire probe. Your 2-wire device is just a loop-powered device, meaning that you have your current coming in one terminal and out the other, and it uses the voltage drop on the device in order to power it up. A 3-wire device has the current coming in one terminal and out the other terminal, and it just uses that to control the current or to read the current, depending on if it's a transmitter or a receiver. And the third terminal is most often used for externally powering it. So it doesn't take a voltage drop off of the loop in order to power itself. It's using some other power supply in order to be powered. So I brought this slide up so that I could show you the circuit very briefly here. So if you will bear with me one moment. Essentially what a 3-wire device has, and I hope you can all see my markings here, is another terminal here, which is going to be your power in. And I actually drew it in the wrong location. It should actually come out of there. So the idea is that you end up having 3 terminals. You have an external power input. You have the current that's coming into your device. And then you have a shared common between those 2 points. So if I can do a little better job of drawing it there for you, you'd have your current input. I should have drawn it on one of these receiver devices. You have your current output. And then you'd have some kind of third terminal coming on there, which is going to take your power. And these would be actual, usually screw terminals that you connect up to. So that's how you would wire them. The thing I will make sure to mention about 3-wire devices is that because you have that shared negative, you have that shared common, you have to be careful that you're not going to start running into ground loop issues. That's not going to be a problem if you just have this one loop and everything in it only connects to this one loop. But again, if you start connecting this up to, say, a PLC with 4 to 20 milliamp inputs, you need to start considering what the isolation requirements are going to be for the PLC. Hopefully that clears that issue up a little bit.
Okay, good. Hey, that was good drawing on the slide. Joey didn't even practice that. Good job.
Well, it's tough using the mouse to draw, but hopefully people will forgive my drawings.
Yeah, okay. We have a question from Thomas. Thomas asks, will more than one receiver distort the reading of the output reading?
I assume you mean the output from the transmitter, and the answer is it won't. Because we're back to the idea of a current being the same everywhere in the loop, you don't have any kind of distortion there. At any point along there, the current going into the first receiver, into the second receiver, into the third receiver, back to the power supply, all of those currents are exactly the same. So that's not a problem, and that's actually one of the advantages of the current loop, is that you can add in all these other devices, just quickly connect them all up in series, and you don't have any problems.
Okay, good. Here's a question from Tristan. Is it possible to get ground loops in a 4 to 20 milliamp DC circuit, or is that really only an AC problem?
No, you can definitely get ground loops. Now, just to clarify, by ground loop, I essentially mean any time that you have the common pins on devices that aren't isolated, and you start getting shared current amongst those. That's usually drawn in the circuits as a ground. And you can absolutely get those if you have multiple loops going into a device that where, let's say my PLC has 4 to 20 inputs and my negative terminals are actually all the same common, and I wire that up to a single power supply that's running all 4 of those loops. Depending on how I wire that, I could see that all my signals are averaged together, because essentially I'm sharing current amongst all my loops. I've destroyed the individual isolation of having one 4 to 20 milliamp current loop carrying one piece of information.
Okay, good. We have a question from Michael. His question is a 4 to 20 milliamp loop especially susceptible to certain kinds of noise, for example, EM or RF? And there's been a few questions about noise and how it affects a 4 to 20 milliamp signal.
Well, I wouldn't say it's particularly acceptable to any one type of noise. I'll say that generally in process industries, you know, as the operators, installers, controllers, you know where those noise hotspots are, and you're going to affect almost any kind of signal you run through an extremely noisy environment. But in most cases, a 4 to 20 milliamp signal is fairly noise immune. There's, of course, always steps you can take to minimize that. You can use shielded cable so that you have a shielded ground around it to try to absorb some of that noise. You can use devices that have built-in filtering, which has the ability to eliminate noise that is there and is getting onto the lines through either hardware or software filtering built into the units. And in most cases, if you do those two things, I don't think you're going to find noise as a problem. It's not like a millivolt system where the noise is so going to affect the signal so badly, there's no way for a device to tell the difference between the noise and the actual signal. If I have a millivolt output system and I put millivolt levels of noise on it, you can see where that's going to be an issue. If I put millivolt levels of noise and generate microamp levels of noise onto a milliamp loop, it's fairly easy to filter that out. So I guess the answer is I haven't found that a 4 to 20 line is susceptible to any one specific source of noise or one specific waveform of noise. However, if you expect you are going to have noise problems, shield your wires and make sure you use devices that have some form of built-in noise immunity, either hardware filtering, firmware or software filtering, or both.
Okay. And a follow-up comment / question. This will be the last one, then we'll have to go ahead and wrap up. This is from Bill. Bill says, by twisting the wire instead of straight runs, will that help with the noise?
Yes, it will. It's a complicated answer as to why for the purposes of this webinar, but it will absolutely help with the noise, yes.
Okay, we'll go ahead and wrap it up. Those were great questions. I know we didn't get to all of them, and we will get back to you via email or even possibly phone with answers to the questions that we did not get to.
Make sure that we have your contact information if you asked a question we didn't get back to.
Yeah, and we'll get that in the, I think the webinar saves that too, Joe. So
okay.
We should be good there. Okay, what's the next slide? Oh, next webinar. Next webinar is November 18th, same format as this one. The title is Loop-Powered Meters, the Fundamentals. And this will be all about loop power. Oops, we went to the back to the slide.
Sorry about that.
The next webinar will be all about loop power. And you'll learn about the key criteria for specifying loop power. You'll learn about loop power devices, can you use them, and you'll learn how to decide if a loop power device is your best choice. So November 18th, everybody who registered for this webinar will get an invitation to the next one, and it'll be the same process as this one. Just click on the registration page and fill it out, and you'll get all the follow-ups and everything. And again, this is presented by Precision Digital. And if you do need some help, perhaps questions, or need to buy a loop-powered meter, a digital panel meter, explosion-proof instruments, large display meters, please give us a call. We'd love to hear from you. And with that, our contact information is also included. Again, everybody will get a copy of the slides and a link to the recording via email. And then in a few days, you'll be able to also access it and share it on the Precision Digital website. And thank you very much for spending time with us today. We sure appreciate it, and we hope you found this useful. There will be a survey you'll get automatically after we close out the webinar. Feedback is appreciated. Let us know what you liked. Let us know how we can make it better, and we will incorporate it into the next one. Thanks, everyone. Have a great day. And again, thank you for coming. We'll see you next time. Signing off.